Good. Okay, so this is basically 1 hour summary of what I covered during this semester, half of the semester, at least. So here's the outline. So I'm going to start with some background and information, and then some decision theory, introduce some decision theory for finding optimal decisions, and then introduce some method, popular methods such as Q-learning and A-learning and G-estimation. And then I like to briefly make some connection with the reinforcement learning, and then end with some conclusion and advertisement. So the personalized medicine is a very hot area and important area in medical domain, and the heterogeneity. Oops, sorry. Okay, can I? Let's do it again. Okay, sorry. Okay, heterogeneity means that the effect of the drug could be different, right? So, so one drug can be good for female, turns out to be bad for male, something like that. I mean, for example. So both in terms of the primary something's not really, sorry. Let me fix, okay. Primary outcome and side effect. And then personalized medicine is a kind of a new paradigm that emphasizes the systematic use of individual patient information to optimize that patient's healthcare. So the idea is we wish to combine decision theory with the data, right? Decision theory and data. That's basically bottom line. And so then to do any decision theory, we need to first have a suitable utility function, right? So utility function should be defined first based on the context of the problem. And then we have some rule for how to find the optimal decision that maximizes minimize the loss function, for example, right? And then second part is how to estimate the utility function from the data. So that is the kind of bottom line. And nowadays, there's actually a very interesting concept, something called the prescriptive inference or prescriptive analytics. So if you search Google, what is the prescriptive analytic, there's a lot of things going on. Basically, people kind of saying that there's a data science evolving from the descriptive to predictive, and then from the predictive to prescriptive. So descriptive is basically very simple, right? Mean and variance, and but predictive is still we want to predict some future outcome under the same population. So we are still in the predictive inference, you are still thinking of the single universe, right? But the prescriptive inference is try to answer what if question. What if I choose 621 instead of 5, something else, right? Then my life will be changed, right? Something like that. So that is actually kind of a multiverse. It's not really a universe. It's a multiverse kind of situation. There's a recent movie, Everywhere, Anywhere, something like that. I don't know the title exactly, but anyway, yeah, that is an interesting concept at least. So then, what is the key concept in the prescriptive inference? Where we have some potential outcome, right? So potential outcome that defines the causal parameter. So the causal parameter is the parameter that answers my what if question, right? So, so that depends on my choice. And then to estimate the causal parameter, we introduce a model and estimate the parameters in the model. So that is actually nuisance parameter. So it's like, suppose if you think about imputation context, you are interested in estimating the population mean, for example, but to do imputation, right, to make the imputation, you need a prediction model. So that prediction model could be nuisance parameter, essentially. So to estimate the nuisance parameter from the observed data, so tricky part is that nuisance parameter is a kind of a systematic behavior of the potential outcomes, while our observed data is different from the potential outcome, right? So then we need to make the connection between the realized data and my potential outcome. So that make a connection is sometimes called identification problem. Okay. So this is the very basic review of the potential outcome framework. So the concept was started from Neumann, and then Professor Rubin used that concept and disseminated a lot. So suppose we have we observe X and A and Y. So X is a feature, A is a treatment option, like drug, right? And then Y is a realized outcome variable for patient. And then Y star is so YI is observed data, while YI star is the potential outcome based on the your treatment. So then this kind of assumption is often called the suitable assumption, and which is basically consistency condition. And we are interested in finding the optimal decision rule that such that this guy is sometimes is called the value, right? So this value is maximized, where the value is the expected potential outcome for the as a function of your decision rule. So your decision rule it has an input of X to output to action, right? You have an action space and you have a feature space. So from the feature space to action space is a decision rule. And based on your decision rule, you can either observe Y1 star or Y0 star. But because of the systematic nature of the distribution, so this one involves some, so this is a causal parameter, right? This is one example of the causal parameter. Okay. And then the basic decision theory says that we should use the conditional expectation. So we should choose the option that maximizes the conditional expectation of the potential outcome given the features. So that is the basic decision theory. So then the problem reduces to estimating this conditional expectation. So estimating the conditional expectation from the data is essentially identification problem. So we use this identification result in 3 to estimate the conditional distribution, and then use this conditional distribution to find the optimal decision, right? So that is the very basic idea for this kind of decision rule. And then for these identification conditions, we have a suitable condition and NUC condition and positivity assumption, right? So these are 3 assumptions are important key identification conditions. And NUC is the most critical one. So so basically, X is a confounding factor, right? Confounder that affects both choice and the outcome, right? So our causal question, right? Our causal question is estimating this relationship. So this is our parameter that we want to compute, estimate. But end of the day, the problem is that this X interferes, right? And so that means we need to use conditional on this compounder. So that means we should use that compounder into the model, and there should be no other confounders, right? There should be no, so all the confounders are observed and available to us. So that is the assumption behind this theory. Okay, and now this idea, this this part is just a single decision rule, but now I'm gonna move on to more challenging case of the multiple decisions. So multi-stage decisions and dynamic treatment regime. So in many cases, especially in the medical, you have patients, right? You have patients visiting multiple times, and then we want to see applied treatment based on the progress of the patients, and so decisions can are made in multiple stages in real cases. So in that case, we use we are interested in developing dynamic treatment regime, which is a sequence of decision rules, and one per stage of intervention for adopting a treatment plan to the time-varying state of an individual subject. So state is a kind of X, okay, but your X changes over time. And each decision rule takes the subject individual characteristics and treatment history observed up to that stage as inputs and outputs the recommended treatment at that stage. Recommendations can include treatment type, dosage, and timing. And now the decision rule, DJ, at J's stage is a mapping from the history to action space, right? Where HJ is the history space and AJ is the action space at the J's decision. And there's a more complicated situation, but we'll only consider deterministic policy in the sense that the decision mapping is not stochastic. So here's a toy example, t equal 2. So suppose that we are two decision point with action space A1 and A2. And then baseline auxiliary variable is X1. And then X2 star is a potential intermediate outcome or state on the A1 equal to a small a1, right? So based on my choice in the first decision, my state at second can be changed, right? So it makes sense to use AI. So star means that it's a potential outcome, and then Y is also potential outcome, and that is a final outcome or reward. So you want to evaluate, right? End of the day, you have an evaluation, and so that under the choices. So then we have so many potential outcomes. So we have a potential outcomes of X2 and 4 potential outcomes of Y, because we have four possible combinations for under the 2 decisions, right? But the observed data itself is just the X1, X2, A1, A2, Y. So that is our observation. Then the goal is we are interested in finding the optimal decision rule, D1 and D2, such that the value is maximized. Okay. So then really this is the kind of how we our choices create a multiple population, right? Essentially. So at each decision point we choose only one, and so then we either observe the X2 1 or X2 star 0, right? We choose observe only one of them, and then at the second decision rule we also choose one of the 2, and so we end up observing only one of the 4 possible outcomes. Okay, so then now question is how to find the optimal decision rule. Well, for J equal 2 is okay, because we can still so basically using the basic decision theory that I show you I showed here, right? So using the basic decision theory, if I observe everything, then I can basically if I observe every covariate information, then I can conditional on all the history and then choose the option that maximizes the conditional expectation. So D equal 2, that is not really difficult. And also the equality here is holds because so the first conditional expectation is about with respect to the potential outcome, while the second one is with respect to the observed data, right? By the way, this one doesn't have to be. Yeah. So anyway, so this equality is essentially the result of the identification condition. However, now the question is how you want to choose the optimal decision for J equal 1. It's more tricky because if you naively want to apply this one, the problem is that you don't really observe x2 star at A equal, right, at the decision 1. So x2 is actually confounder for the causal path from A to Y, but it is a mediator in the causal path from A1 to Y. Okay, so here's a graph. So basically, if I'm interested in investigating this arrow, right, then the role of x2 is a confounder, right? Because x2 affects both A2 and Y. So and then you have only to include the confounder into the model, and then the confounding effect can be controlled, right? So basically, as long as we can include x2 into our model, so the selection bias disappears. So it's okay. But in my now I'm into now. What about the mapping from a what about the relationship from A1 to Y? So from A1 to Y, we have 3 passes. One is this pass, but this pass is not really big deal because we already, right? So A2 basically block this pass, no problem. And then second one, this part is okay also because I have a direct connection, so I can basically use this path to determine. The tricky part is this one. So A2 is related to Y through x2. So that is a mediator, and this mediator is not observed. So we cannot really. So basically, we cannot really use this one to do optimal decision. Rather, we want to average out, average over possible x1, x2 in order to make the optimal decision. So here's the answer. So this is basically the correct decision theory that we need to apply in order for the multiple decision rule. So basically, here's the we need to first understand how to evaluate the effect of the so how to evaluate the value, I mean expected reward. So sorry. Okay. So basically given D. So given D, I can, so D is just a rule, right? To how to assign my A, how to assign my history to A's. So this is the expected reward conditional on history at 1, while the second one is the expected reward at the expected reward at the time of second decision, right? So this is a stage 1. So we have because we have two stages. So for each stage, I have a different information. So basically, I want to evaluate the value under the D. given my history. Okay. And then the optimal decision, so optimal value function is basically choosing this. And then there's an interesting, so the optimal, so this so the superscript OPT is the one that maximizes the value expected reward, right? At each stage. So at and then one important result is, this is probably the most important result in DTR, is that my best decision at D at 1 should use my best decision at stage 2, right? So basically this one, so this is, we first find the optimal decision at stage 2 and then use that, because use that to carry backward to make the decision on A1. So this equation is called Bellman equation. So this Bellman equation is very famous result in reinforcement learning, and basically we'll see it more clear later. But this is a basic result that we want to use.
When you define A2,
Right.
so it's expectation with respect to small d.
Right.
And so basically that means that A2 chosen from D. It's chosen based on D.
So D is a deterministic function.
Right.
A deterministic function. And so I guess so the real random variable is a potential outcome. So the expect, so given, so what is the real random variable is a potential outcome x2 star and y star, right? And then A1 and A2 given x1. So
But the A2 is determined by
so I'm sorry.
A2, yeah, the capital A2 is a random variable.
Right.
That is a action taken under D.
On the D, right. So D, so this is basically okay, mapping, right? I mean, D1 is just is 1 or 0 under something like that, right?
Right.
So so you,
so D is an action which ensures the potential outcome. Basically, those are random variables. So if you fix D, then I think you know which potential outcome you are realizing, but the expectation is over those random variables.
right.
Is that right?
Yeah, right.
So you're saying that A1 and A2 are not random variables?
This is determined by D.
No, A2 is a random variable.
A2 is random. A1, A2 are random. Should be, right?
And the random favors the deterministic function D.
D, yeah.
Right.
So the input of D is random.
Yeah.
So, but yeah, I think that A2 probably is equal to like D H1. So
So H is random.
So I guess I see what you mean. So this one actually, the only thing, so in my class sorry, in my class I defined potential outcome under the derived from potential outcome, right? As a function of A. But here, this notation. So basically, another way of writing this one is just if you write it potential outcome of the under the D1 and D2, right? X1. That should be so that's more consistent with my notation in my class, but I didn't want to introduce additional notation in today. So
So what is
Yeah.
the difference then here? So you are writing in terms of A1 and A2, but in
no,
terms
so this one, so if basically this is just another way of writing this one.
is the A1 determined by D, expectation in terms of D, right?
Well, this is given. So the definition of this guy is just this guy.
Okay.
Okay.
This is another way.
Right. So and then okay. So okay, some remark. So instead of using using this definition of the value function is original Bellman's Bellman equation, but it's more convenient to use the Q function, and the Q stands for the quality of action. So basically we write it as so value is just a function of H, but here Q is a function given H, we want to write it in terms of the option, okay? And basically that way we can actually want to optimize, find the maximizer of A over A. So so then this is, so in my class I didn't include, it's not really my fault. David Young lecture note also didn't, but this one is more accurate. So basically we should define the Q function for a given policy, okay, and then we want to evaluate the potential, so evaluate the value function, so expected value, so which is the expected reward, right, given the history and the option that I'm going to use, right? And so then basically Q1 refers to the want to quantify the quality of action at decision 1, while Q2 is a quality, right, of action that I want to use at decision 2. Okay. So interesting part is that Q2 D doesn't depend on D. Okay, because of the identification condition. So because of this, right? Because of the second equality, it doesn't. So end of the day, it doesn't really depend, because in the last, right? In the last stage, nothing is given, right? I mean, the decision doesn't play any effect. Given decision does not play any effect to me, because the concept is we want to basically at stage J, we use the history, right? So at stage J, we use history up to J, and then we want to evaluate the action at J, and then after that, I will follow given D, right? So this is the, so basically that's why we have a, yeah.
H2A2 is equal to Q2 H2A2. So if A2 equal to D H1, because that action being taken as A2 should match with the policy given for like E2 D.
Are you talking about the first Q1 or Q2?
Q2.
Q2, and what is your point?
Yeah, my point is that the definition of Q2D with the superscript D. So that definition, the A2 and the D should match. The
Well,
A- the
that-
small A2 and the small D
well,
should
my point is that, so the definition of Q has a superscript because we want to evaluate the effect of the given D.
Right.
Okay, and then but always the last action is free of given D. Right, the last because it doesn't really, there's no policy to follow, and the last, because see here's a, so suppose I have a 3 decision, okay, and then the last one I want to choose. So basically Q1 is a A1, D2, D3. Q2 is a A1, A2, D3. Q3 is a A1, A2, A3. Right? See what I'm saying? So look at, I mean, this is the, I just want to emphasize. So we are talking, so Q function is an evaluation of the reward, expected reward for the particular decision rule. I mean, for the particular counterfactual outcome where we follow all the history, and then before J, and then at J we have a AJ, and then after J we follow the given policy. So that's why Q1 I want to evaluate the effect of A1, and then I assume that I follow all the D2, D3. Q2 I follow D3, but I want to evaluate A2, and A1 is just the history. For Q3, A1, A2 is just the history, and I want to evaluate A3. Okay.
I have the information about D, and I will.
Yeah. So Q1, I'm gonna follow D2, D3, everything. I'm just want to evaluate the A1 only, because I want to choose the optimal one. End of the day, right? Optimal D1, A1.
Then A1 is the history.
So that's just the history, right? For decision 2, my A1 is a history. So I'm not going to change. I cannot really change because it's history. But A2, right? A2, I want to optimize. And then A3 is a given D. Okay. So that way, so that is basic. So that's why this in the last action, right? So the last stage always free of D. And so then we can always backward induction makes sense. And so then we can basically use Q2 and then optimize A2, right? And then use that to take the conditional expectation. So this Bellman equation here 4 can be written as in terms of the Q function. So that is the basically the decision theory. So decision theory can be written in terms of the value function, and then you can equivalently express it in terms of the Q function. And the Q function definition of Q function was not really rigorous in David Ann's textbook notebook. So, but so this one is better. So I decided to follow this approach. So this OPT means that we choose the optimal decision. And then once you have that, you can basically find the optimal DTR in a backward induction way. So so use Q2. So basically here, if Q functions are known, okay. If Q functions are all known, then you can sequentially find the optimal decision, because each each Q function has a history and option, right? Single option. So you have only to optimize with respect to the options, right? So then D2 can be obtained this way, and then use D2 D1 optimal. Oh, sorry. You okay. So you use this guy to here, right? You use this guy to here to obtain this guy, and then maximize Q1 optimal. So Q1 OPT means that this is a particular D. So remember that Q1 has a superscript D, and this particular D I'm going to choose is the one that uses this D2 OPT. Okay. So that basically take care of the basic decision theory. So that is the decision theory part. And one thing that we should remember is that this guy. So what do you mean by this? What do you mean by that we plug in this D2 optimal? That means we are considering conditional expectation of the counterfactual potential outcome, right? Counterfactual potential outcome under this choice, under the optimal choice at D2, at A2, because although, right, that's where, so I know I have a less optimal decision, but I know, so after Q2, right, optimizing Q2, I now have an idea what I should have done, right, for in the future. So it's a kind of weird, should have done in the future. But anyway, I know what my optimal decision would be for the future, and then use that, right, use that to predict my potential outcome under that option, and then try to compute the conditional expectation of that guy and maximize over A1. Sorry, this one should be A1. Okay. So that is basically decision theory. There's no estimation at this point. But now we are moving on to estimation. Yeah. Yeah.
So T is deterministic function.
Right.
So then, for example, if we're talking about the D1, so basically given X1, D1 is deterministic. The D1 is A1, right? Okay. So because that is,
Well, A1. So
if I follow the policy D, then given X1.
but the data does not, there's no guarantee that data follows the optimal decision, right?
Right, but we are not talking about estimation yet.
Right.
We are just talking about
Right.
if they know the Q function, right? We are not talking about the estimation yet. So if you go to the previous page.
Here.
So I'm just thinking about the definition of Q1 with superscript D. Okay, Q1 with superscript D.
Okay.
If we gave an X1, right? So if we gave an X1,
Mm-hmm.
so then A1 is basically fixed because we've given a policy D.
So we are conditional on A because we want to evaluate A1, right? So that's why we conditional on A1.
Right, but my point is, if we given a policy D, right, for a given policy D, so if we given X1, then A1 is also fixed.
Oh, no. We do not follow. That's the key point. Because if you want to evaluate, we want to optimize A1. So we should not follow D1.
Yeah, yeah, I understand. But another way to say that is we can like evaluate Q1D for all possible D.
No, we are not. We are not really following. We are following only future, not the current. Here we are only following future. So optimal. So that is exactly what I'm keep saying. I mean, I'm taking an action A1 and follow the policy D thereafter.
So then it's just like how we define the small D. right? So how we define the small d?
Small d is a whole vector, whole sequence.
Right, so yeah, my only point is that, so that Q1D is
It's
only-
not really the whole vector, that's your saying.
It's only defined when D1 equals to A1, which is fine for the following like optimization.
Well,
But in terms of if they gave the policy, right? If they gave both D1 and D,
okay,
right? So then A1 has to be equal to small D1.
no.
We're given a policy.
So in this definition, no. I mean,
I think you observe all A1, AI1, but that does not follow D1. And based on A1, we wanna find
They are not
optimize.
using any data yet. It's just
Right.
population level.
right,
So
Yeah.
your argument is that if they give A1, they only consider D2 and D3.
right,
Yeah, but my point is that if they given D, they basically given the whole vector D, D1, D2, D3.
right.
And then if we evaluate at A1, so that A1 has to be equal to small d1 for a given policy D. So if we choose another policy, then we can evaluate another A1.
Well, we want to, the whole role of Q1 is to find the best D1.
Right, but we can evaluate Q1D for all possible.
Well,
But the problem with that is that we're trying to make it sequential. And so like we could, like we're trying to evaluate the, kind of, in some sense, trying to evaluate all the policies. But we're trying to do it one at a time. And so this notation tells us what we're looking at the level AI or J. That's what we're evaluating. And we know what we're doing after, so in some we're saying we're not testing. So I mean, if we go through all of the Q functions, we are evaluating kind of every step in some things. But
okay, well, let's move on. We have some other things. So, okay, so, well, the definition of Q1, yeah, okay, let's move on. So Q-learning is nothing but estimating Q functions, Q2 and Q1 using the data. And so Q2, no problem, right? Because we have all the identification condition holes. So we just use data, observed data to estimate Q2 and then optimize. So once you do that, then what we want is to compute this guy, right? V2 OPT. So V2 OPT is a predictor of the potential outcome on the best option at D2. So that is this guy, right? So I use Q2 and then evaluate it D2 OPT and then use it as if it is an outcome variable. So that is sometimes called pseudo outcome, and then do the regression of the using A1 only, right? I mean H1 and A1 only to compute Q1 OPT, and then Q1 OPT can be used to obtain my optimal decision for D1. So that is the Q-learning, and and so here's some remark. So model for Q2 is for the observed data, right? We just have no adjustment, just use the standard regularized, standard regression like lasso or whatever. We just use that. But Q1, so we are not really computing the Q1 of the observed data. Rather, we want to compute the Q1 under the optimal T2, right? So that's why we need to use this outcome, or this could be a better. So this is what? This is my current Y, and this is my expected one on the optimal decision, and this is the expected one under my current choice. So that these two consist my improvement on the advantage that I could achieve on the optimal decision. So sometimes this is called the regret function or advantage. So basically, the point is that if we know D2 optimal, right? If we know D2 optimal, then I can change my Y value so that on the optimal decision, so that it can become a counter predictor of the counterfactual outcome. So that is very close. So now we're going to move on to A learning. So A learning directly use that advantage function concept directly. And so here, what is the advantage regret, right? So I have two choices. So that means I can actually decompose my regret into two parts, right? What is the regret due to my decision at stage 1 or the regret at stage 2, right? So my regret can be decomposed. So if I choose best way at the time, then I have 0 regret, something like that. So then basically here's a so U2 is, of course, U2 is my regret at decision 2, right? So then A1 is just the history. So it doesn't really play any role, right? And then my difference is the potential outcome, expected potential outcome on the optimal decision versus my current, right? I mean, on the A2, under the choice of A2. So this, and then idea is we want to make a parametric model for this advantage, because we know that it should be 0 if the model is if I choose the best one, and then greater than, right, greater than 0. So this kind of model turns out to be called structural nested mean model, and where the structure is used to indicate that the model is for the counterfactual quantity, and so counterfactual quantity on the optimal decision in the future. So it's a capture the causal relationship. So SNMM parameterizes the causal effect, that is the difference between the conditional expectation of the outcome in the observed data and the conditional expectation of the outcome under some potential outcome scenario. Right? Because I cannot really observe one, right? But suppose I want to compare between the two choices, right? So then this is belongs to essentially some structural modeling. And then SNMM so here's one simple way to model this kind of approach is used to contrast the function, which is essentially computing the difference between the Q functions. So at decision 2, right, stage 2 is just the Q2 minus Q1. I mean Q2 A2 minus Q2 0. And then decision is just maximizing C2. And then from that, I obtain optimal D2. And then use that to plug in, right? Plug in. And so this is my counterfactual difference on the optimal decision at D2. And so this is becomes a kind of parametric. So a kind of interesting model. So it becomes a semi-parametric model where your model for Q optimal is a Q0 plus contrast function, so blip function, and then we want to use a parametric model for contrast and fully non-parametric for the baseline. Okay, and then James Robbins, he invented the whole framework, and so end of the day, his idea was, okay, we use this. So start with the D2 first, because T equal 2, last stage, we have an identification problem already. So we just use this semi-parametric regression model, and we make it kind of a double multiply something has zero expectation to make a doubly robust. So doubly robust means that either pi2 model or nu2 model are correct, then they are consistent. But we do need correct. So we have 3 models, but one of the 2 is correct, then we are good. So T equal 2, we don't have any real difficulty, just a semi-parametric estimation. And then use semi-parametric model to obtain beta hat 2, and then find the optimal decision. And then use that to modify my y to reflect my regret. Okay. So you observe y, but I know that my y does not necessarily come from the optimal decision, right? So then we need to estimate the regret and then modify. So that is I now have an idea why he used G. What do you guess? No. Well, could be, but I think it is generative. So he's really genius. I mean, he already had this concept. Basically, he wants to impute the potential counterfactual outcome, right? And so then it's different from just the imputation, right? Because we want, what if we are really talking about what if situation? What if I had the best choice? Then what my y will be something like this, right? So that is the pseudo value, and then use the pseudo value as if y, and fit the regression, and then you compute the beta hat 1, and then use that to obtain T1 hat optimal, right? So that is the G estimation formula, and so he already kind of foresee the AI generative model at that time. I think I'm kind of late. Oh no, not really late. So I will skip. It has a good connection with the reinforcement learning, but so state is X, action is A, reward is Y. So state, action, and reward are the 3 basic components of the reinforcement learning framework, and but it's a lot of stages, right? So you cannot really make the full model. So you may need some simplification, which uses the Markov property. So basically, you don't want to all dependence on the history, right? You just want the most recent one. So does not depend on the distant past. So so goal of the reinforcement learning is to learn how to map state to actions so as to maximize the total expected future reward. So really has the DTR theory can be used. So the Q learning and A learning can be used in reinforcement learning. Some majors, but there's some differences. So in reinforcement learning, they are mostly work on robot data, so mechanical data. While DTR, we use human data, right? Patient's data. Humans are different from machine, right? So there's a big philosophical difference. For example, machine, we know the mechanism, so we can use the physical law to understand, to build in there some part of the model, but we cannot really build that model into human, right? We don't know the human nature, so so that's one part, and then data are often very cheap because of from the robot, right? But because of cheap, the data can be huge. While in human data, it's expensive, so it cannot be huge, right? So it's a kind of a trade-off. So extremely expensive. So then we need more careful model building, something like that. So anyway,
So, you mean that for reinforcement learning, we don't need to worry too much about the response model? It's mainly based on outcome.
so there's no real response. So in reinforcement learning, we are not really making a model for the reward. Reward is just a function of the. So reward is a little bit different.
Right, but, because they use discount, right, for the future.
Right.
Yeah, but my point is that because it's kind of local, right?
Right.
Systematic. So there probably is now the response model we need to consider as in DTR.
Okay. Yeah, I'm not really. I just use this textbook to make the. So they have the comment. By the way, this book is better than the textbook I used. So if you are interested, I recommend to read this book. Anyway, so it's really promising area research. I checked JASA and keyword search the dynamic treatment regime. I found 220 papers in JASA only. But if you look at but they are in the last 10 years, right? In the last 10 years, 200 papers in JASA on this topic. So really exploding. But if you search in the Journal of Machine Learning and this area, it's 5 times, probably 10 times. So it's really exploding and hard area of research. And also it's still unexplored area. So there may be a lot of research problems remain unsolved, so that we have some chance, right? So anyway, I plan to teach these topics in Step 21 in the future. So here's an advertisement. So I'm gonna change the sequence of the my courses into some a little bit to include the emphasis on the causal inference. So 521 will cover. So like my class so I half semester I teach another one, something like that. So I plan is to before midterm I will cover survey sampling, and then after midterm I will cover causal inference, something like that. 523, it will be a mix of the missing data and projection technique in Hilbert space. 621, it will be DTR and reinforcement learning. So I hope that you guys have an interest and register this course, and if you are interested. So anyway, thank you for your attention.
Very much. See you next week.
Okay.